Hello, welcome to the third part of the first lecture of week 3, and in this lecture we're going to talk about something called the total probability theorem, and this is basically an approach that allows us to compute total probability of things like system failure by breaking it up into a series of simpler bits and pieces. So basically, as I mentioned, we often want to find the total probability of an event such as system failure. So to do this, we can define F to be the event that the system fails, and then identify a series of possible causes of system failure. Let's say we have C1, C2, C3, and so on and so forth. There could be many more, but let's stick to 3 for now, just for simplicity. If we assume that the C's are disjoint and collectively exhaustive, i.e. that we've considered all possible causes of failure, and in general this is important that you do this because it's the causes of system failure that we forget that often lead to, that we forget to design against, that often lead to failure of our systems. So do try to identify all the possible causes. In this case, we can draw a Venn diagram that looks something like this. We've got our sample space consists of the possible causes, and somewhere in there there's a failure event. So given that cause 1 takes place, there's some possibility of a system failure, and that would be the area given here. Similarly, if cause 2 occurs, there's some possibility of failure, and so on and so forth. So what that means is that I can write the probability of failure, the overall probability of failure of the system, this is the total probability of failure of the system, as being made up of bits and pieces. And that is the probability of failure and cause 1 occurs, or probability of failure and cause 2 occurs, that's this region here, or probability of failure and cause 3 occurs, that's what I'm showing here. I'm seeing unions here, so I ask the question, are these disjoint? For the total probability theorem to work, we have to assume that these are disjoint. I'll show you later what happens if they are not disjoint. And it's very possible in general that we could have multiple causes taking place at the same time that could lead to system failure. But let's for the time being assume that these causes are disjoint so that this union turns into 1 plus sign for each union. That means our probability of failure is probability of F given C1 and C1 plus probability of F and C2 plus probability of F intersection C3. And we have a rule for this. It's probability of F given C1 times the probability of C1 plus probability of F given C2 times probability of C2 and so on for C3. And with this, the interpretation of this is what is the probability of failure given that C1 takes place, and we have to weight that by the probability that C1 takes place, and so on and so forth. And the reason I say that this separates into a series of simpler problems is that we can usually compute probability of failure given a specific cause more easily than we can jump straight into the overall probability of failure of a system. And then the only other thing we need to do is figure out how often does that cause take place. And then we weight this component by the fraction of time or the probability that cause takes place. Okay, so the rules to use this approach: causes must be disjoint. And we'll, like I said, we'll discuss shortly what happens if they are not disjoint. The causes must be collectively exhaustive, i.e. a partition. So in other words, I said that you need to consider all possible causes of failure. The ones that you omit are usually the ones that result in failure of system because you haven't designed against it. A very useful graphical technique for the total probability theorem is the event, sometimes called probability trees. I'll call them event trees in this course. And basically what you do is you have one branch for each possible cause, and then off of each of these is my failure versus non-failure branches. So these sub-branches are conditional. So given that I've come out on this branch, C1, so that given that C1 has taken place, probability of failure given C1 leads me to this path here. And if it doesn't fail, I'm on this path here. Okay? So I'm looking for the probability of failure. It's the probability that I arrive here, or here, or here. And the word or is coming in there. That's a union. And basically, if these branches are disjoint, it's the probability of going this path, or this path, or this path. And it turns out that to compute that probability, I just multiply this probability times this probability, plus this probability times this probability, plus this probability times this probability, and I'm showing it all over here. Okay, so probability to go this path, or this path, or this path, and then I just multiply probabilities along the paths to get the overall probability of failure. So this really makes total probability theorem simple. Just draw a tree, figure out which paths you're ending up at, and then add up all the probabilities associated with getting to those endpoints. Rules for the event tree: you cannot be in more than one branch at a time. If you draw an event tree, you should look at it, and if you decide that you can be on more than one branch at the same time, it's not a good event tree. You've got to redefine your events or something. And that basically corresponds to the events being disjoint. The other rule is that the sum of probabilities from any node must all add up to 1. And that means that these possibilities, the causes, are collectively exhaustive. So their probabilities have to add up to 1. And the sub branches also have to have probabilities add up to 1. In our particular case, we got F and F complement, so it's got to be one or the other. So that the probability of that plus the probability of this must be 1. So what happens if the events are not disjoint? Suppose you have two events, or maybe two causes, A and B, and they can both occur at the same time. So our picture looks like this. They overlap. In which case, then you have one branch for each disjoint area. So if I got a situation like this, first step is going to be draw the Venn diagram. Then you know you've got one branch for each disjoint area, and there are 4 disjoint areas in this picture. Outside, this is A alone, A and B alone. Okay, so you're going to have a branch starting for the intersection, a branch for A intersection B. Then you got a branch for A intersection B complement, which is A alone, and then you've got a branch for this is a mistake. Hang on a minute. This should be A complement intersection B. So let me just erase this. Okay. A complement intersection B is the B alone. And then the last one is everything outside, which is A complement intersection B complement. Okay. So you can see if you've got 3 events and they all overlap, you can get a event tree that becomes very complicated very quickly. So with any luck, you have a situation where these events are disjoint. Let's illustrate this, the whole concept with an example. Let's suppose that a major nuclear fusion facility has been proposed for Nova Scotia, and we're evaluating the chances that it receives funding. And that depends on which political party is elected in the next federal election. It's estimated that if the Liberals get in, the probability of funding is 60%, Conservatives get in 40%, and the NDP get in, it rises to 70%. Assume this is a partition. What that means is that are these the only 3 parties that can be elected in the next federal election? Well, generally they're not. There are usually other parties like the Green Party, and we're ignoring them. If the probability of these other parties being elected is sufficiently small, that's a reasonable approximation. But if it's not, you have to include those other possibilities. For now, let's just assume that there's only these 3 possibilities for simplicity. Okay, so let's suppose that we've conducted a poll and we've evaluated the probability that the 3 parties will be elected. Probably the Liberals will be elected is 55%, probably the Conservatives are elected is 15%, and the probability that the NDP gets elected is 30%. Then what is the probability that the facility gets funding? This is the sort of exercise that you would go through, because if this probability is small, you may not want to bother spending a couple $1 million on a project proposal to submit. It may not be worth spending the money on the proposal. Okay, so I mentioned this business about the partition. Let's define some events. Let's L be the event that the Liberals are elected, C the event that the Conservatives are elected, N is the event that the NDP are elected, and F is the event that the facility is funded. From that, I can write out the given information. So I'm told the probability that the Conservatives get in is 55, no, sorry, the Liberals get in is 60. Oh no, that's those are the conditionals. The probability the Liberals are elected is 55%, Conservative elected is 15%, and the NDP elected is 30%. So I can write that down. 55% for Liberals, 15% for Conservatives, and 30% for the NDP. Then I can look at probably a funding given these three parties. That comes for the first part of this thing. If the Liberals get in, probably a funding is 60%. By the way, I should point out if something happens is another way of putting given that something happens. So look for that sort of keyword. If something happens, blah, 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 that means that you got probably of F given Liberals is 60%, probably of F given that the Conservatives get in is 40%, and probably of F given the NDP is 70%. And from this, I can now construct an event tree. I can say, okay, I've got three original branches that the Liberals get in, Conservatives get in, NDP get in, and the probabilities of these are labeled on the branches. Then I've got conditional probabilities, probably of funding given that I'm on branch L is 60%, that's this number, and non-funding is 40%, so that these things add up to 1. And you should check these too, make sure they add up to 1. So I got 0.3, 0.45, and that adds up to 1. So I add all the probabilities in here, and now I'm looking for a probability of getting here, or here, or here. And that's going to be this product, 0.55 times 0.6, or plus 0.15 times 0.4, and plus 0.3 times 0.7, which are these numbers here. And the probability of funding then is 60%. So that's reasonably high. It may be worth spending some money on preparing a proposal. You don't have to draw an event tree, although I would recommend you do because it simplifies things. You can use the total probability theorem directly. Probability of F is probability of F given L times probability of L, and you just cycle through the various conditional events here, and then plug in the numbers, and you get the same answer. And I think that concludes this lecture. So thank you for listening.